Hello, my name is Gabriel Istrate, and I'm going to present my work with my colleagues Cosmin, Bonchis, and Adrian Craciun on kernelization, proof complexity, and social choice. So, I like tapas in real life and in research, and combining different research areas is a nice way to learn about lots of cool stuff. So I said in this paper that to understand what we're doing, you need a little bit out of three research areas, and I realized preparing these slides that I was wrong. You need a couple of notions from four different areas. So these are proof complexity, and then parameterized complexity, specifically kernelization, and computational social choice, and last but not least, combinatorial algebraic topology. In a nutshell, what we do in this paper is we see how notions from parameterized complexity can help us obtain efficient propositional proofs, and we apply this to proof complexity of statements from computational social choice and continue our work on statements from combinatorial algebraic topology. And because of this diverse background that's required, I'm not going to insist on technical details. I hope to be able to convey the general philosophy, and I'm not going to fully present all the results in the paper. So the starting point is propositional proof complexity. We're talking here about unsatisfiable formulas, and we want to prove they're unsatisfiable. And of course, you can do that by example resolution, and you can talk about the complexity of such a proof, which is the minimum length of a proof. And of course, resolution is quite limited. Proof complexity has concentrated on some more powerful proof systems, including some which we don't know how to prove exponential lower bounds for. And the proof system that we're interested in is the so-called Frege proofs. And to define it, we can take a look at the so-called Hilbert-Ackermann proof system. It has the usual ones: proposition variables, connectives, a couple of axiom schemata, and one inference rule. And the choice of this is not really important because there is a result, a classical result of Cook and Reckau, that show that to some extent all Frege proof systems are equivalent in the sense that they all simulate each other with a polynomial overhead. And the problem that motivated us was the problem of separating Frege versus extended Frege proof systems. So what's an extended Frege proof system? It's a Frege proof system where you're allowed to do variable substitutions, that is, substitute new variables for formulas. Of course, this won't help you prove more things, but it may allow you to prove things more efficiently in terms of the length of the smallest proof. And the question is, can we come up with formulas that for which extended Frege is exponentially more powerful than Frege? This is a classical problem that was discussed by Bonnet, Abbas, and Pitassi. And a lot of natural formulas have been proposed in the literature, and most of them have turned out to have quasi-polynomial, that is, sub-exponential Frege proofs, so they don't really, they're not candidates for such a separation. And there are a couple of examples, and there are more examples than the ones that I give here. Okay, now a 2-minute course on parameterized complexity. So we're going to start with the observation that many problems in NP or in co-NP are actually parameterized. For instance, when you're talking about an instance of vertex cover, you're given a graph, but you're also given an integer k. And you want to decide whether the graph has a vertex cover of size at most k. So parameterized complexity is the study of such parameterized problems, and the gold standard of tractability, called fixed parameter tractability, is giving algorithms whose complexity may depend exponentially on the parameter, but polynomial on input size. So we don't want the parameter and the input size to mix. And one classical method to achieve such fixed parameter tractability results is via so-called kernelization, which is a method that basically reduces an instance of a parameterized problem to a smaller kernel instance in such a way that the original instance is satisfiable if and only if the kernel instance is satisfiable. And crucially, for fixed values of the parameter, this kernel instance is small. It has, upper bound depending on the parameter value as well, only, and not on the instance size. So in other words, you can solve all the problems for fixed k by brute forcing a finite number of kernel instances. And kernelization itself is often achieved by what's known as a data reduction algorithm. And the data reduction is basically an algorithm that maps an instance xk to a smaller instance x prime k prime in such a way that it preserves the answer and the instance is smaller. And you can apply a data reduction several times. In fact, you may have multiple data reductions at one time, and you can create a data reduction chain where the first instance in the chain is the original instance. The last one is a kernel instance for all the rules. You cannot reduce it anymore. And one instance follows from the previous one by applying one of these reduction rules. Okay, so this is pretty standard in the theory of kernelization. Now, the main idea of our results is actually quite simple. We're looking at a negative instance, xk, of a parameterized problem in NP. Think of the set of all graphs and parameters k such that the graph G does not have a vertex cover of size k. Of course, you can canonically map such an instance to an unsatisfiable formula. And now let's consider a data reduction for a problem. And if one could translate this data reduction propositionally in such a way that we can create efficient proofs of soundness of each data reduction step, if we concatenate these propositional proofs of soundness of the reduction steps with the brute force proof of the kernel, then you obtain a efficient propositional proof for the propositional formulation of the original instance. Okay, quite simple. In fact, this is not really the way things are done to propositionally simulate mathematical proofs by data reduction. There are a couple of more details that make things a little bit more complicated. For instance, this formula phi may be constructed from the previous formula by a case construction. And now you typically argue in a mathematical proof that one of these cases applies. So you basically have like a tautology that expresses this case construction. And of course, when you do something like a translation of this, you also need the proof of this tautology. And now applying the data reduction with a case will create one formula. And the formula itself is going to be in fewer variables, but it's going to assume that you've made some variable substitution. You're going to, to make it an instance of the same problem, you're going to have to make some sort of variable substitution. So now if you put all the things together, you may simulate a proof, a mathematical proof via data reduction by a tree of propositional entailments. You don't really need this. You can get away with just a chain, but it won't hurt for our purposes. And for Frege proofs, it will turn out that the height of the tree will dictate the proof size. Of course, you also want the tree to have an arity that is bounded, upper bounded by some constant. And now the proof of the formula will consist of all the proof of entailments of each branch in the tree, plus the proof of tautologies that are applied for branching, plus a proof of brute force statements of the kernel instances at the leaves of the tree. And if the tree arity is upper bounded by a constant and the number of nodes is exponential in the height, and as long as the height is logarithmic, this is polynomial. And this is something pretty standard that has been done also in other proofs in proof complexity. If you unwind the substitutions implicit in a reduction step, basically you're still okay. You're going to get a quasi-polynomial proof as long as the height of the tree is going to be logarithmic. Okay, so this is it. And putting all these ideas together, one can state a main meta theorem. It's a little bit too cumbersome to precisely state, but the gist of it is that if you can witness the soundness of reduction rules in Frege, and if you can create a data reduction where the length of the reduction chain is constant, then you can witness the unsatisfiability of the propositional translations using polynomial size Frege proofs. And if you want to get quasi-polynomial proofs, then you can afford getting like the reduction chain, which is logarithmic in the formula size. And normally, simulating this idea along one chain will get you a polynomial size extended Frege proof if you confine your tree to have polynomial height. So this is the general philosophy that we're going to apply, and we're going to apply this to several problems. So one of the problems that we want to apply comes from combinatorial topology, and to explain this, I'll have to start with what was known as Kneser's conjecture, which stated that if you color the subsets of 1 to up to n with n minus 2k plus 1 colors, then there are two disjoint sets A and B that have the same color. Now, this was conjectured in 1955 by Kneser. It's a generalization of the pigeonhole principle. The cases k equal 2 and 3 had combinatorial proofs, but the cases k greater or equal than 4 were only proved in 1977 by Lovas and Barani, and their proofs used algebraic topology, things like the Borsuk-Ulam theorem and the like. And it's true that there are combinatorial proofs have appeared in the meantime, but these combinatorial proofs deal with exponential objects, and they basically hide the algebraic topology behind the combinatorial language. And no efficient purely combinatorial mathematical proof was known. So Kneser can be viewed as a statement of a chromatic number of a certain graph where vertices are sets. For instance, in this example, the universe has 5 elements, and the sets have 2 elements. So we get the Peterson graph, and 2 vertices correspond to 2 disjoint that are connected by an edge correspond to 2 disjoint sets. And of course, Peterson's graph has chromatic number 3, so Kneser generalizes a claim that Peterson's graph has chromatic number 3. Of course, now you can view that the inner cycle already has chromatic number 3. So you can think whether one can get something more strong than Kneser that would quantify this, and indeed that can be done. You can call a set with k elements to be stable if it doesn't contain 2 consecutive elements on the circle, that is I and I plus 1, but also n and 1. And Schreiber's theorem is a generalization of Kneser's theorem that proved that the chromatic number of this stable Kneser subgraph, which is a subgraph of the Kneser graph, is also n minus 2k plus 2. Of course, the part that's interesting is that it is strictly greater than n minus 2k plus 1, because one can come up quite easily with a construction that will color such a graph with n minus 2k plus 2 colors. And we proposed to study Kneser-Lovász theorem in a SAT paper in 2014, and we proved that in cases that have combinatorial mathematical proofs, you can get Frege and extended Frege proofs. And we followed up this work at ICAL 2015. It appeared in the special issue in Information Computation 2018. We did this with Sam Buss and James Eisenberg and Maria Luisa Bonet. And we proved that for every fixed k, these formulas Kneser n and k have polynomial size extended Frege proofs and quasi-polynomial size Frege proofs. So the Kneser-Lovász theorem is not a candidate for separating Frege and extended Frege. And one idea of this proof was that for every fixed k, we showed that the Naser theorem has an easy combinatorial proof. We didn't give a new proof by passing algebraic topology. We showed that we can reduce an infinite number of cases to the computer verification of a finite number of cases. Okay, so that's sort of the gist of the proof. And in this paper, applying our main theorem, we show that similar results in terms of complexity hold for the formulas encoding the stronger Schreiber's theorem. And we do a data reduction of length order log n, and of course, this will give us quasi-polynomial size Frege proofs. And the way to do it is we define a color class of the graph, of the shape of the Schreiber graph, to be star-shaped. Remember that vertices correspond to sets, and we call a color class to be star-shaped if all the sets colored with that color have an element in common. And there is a theorem of Talbot that gives an upper bound on the size of a color class that is not star-shaped. We can't really make use of this result because we will need to simulate it propositionally. Instead, we prove the weaker version, which we can actually simulate propositionally. So we prove that if C is a color class in the Schreiber graph that is not star-shaped, then it has this upper bound on its cardinality. And then the proof goes by showing that essentially, if we had a n-2k plus 1 coloring of the Schreiber graph with parameters n and k, then we can basically drop theta of n color classes and theta of n elements corresponding to that intersection of those star-shaped color classes. So we have theta of n star-shaped color classes, and that allows us to do a reduction, which is of length log n, and which gives us quasi-polynomial Frege proof. And now the paper has more applications of kernelization techniques to prove complexity, and it's done for a variety of problems such as vertex cover, dual coloring, which is a different parameterization of coloring. Rather than talking about a graph and its chromatic number as a parameter, we're talking about a parameter k, and a graph with parameter k, the instance is satisfiable if the graph can be colored with at most n-k colors. We also talk about some other problems, edge clip cover and de-hitting set, for which kernelizations were known. And in terms of techniques, some of the kernelizations were able to simulate are tweaks of classical ones that you can find in textbooks on kernelizations, although in all these cases, we've actually improved these kernelizations somewhat to obtain our results. So they're not exactly the same kernelization as usual. We need to change them a little bit to make the length of the reduction chain logarithmic or constant. So we can prove, for instance, for vertex cover, we have polynomial size Frege proofs. So we have and for edge clip cover, we have polynomial size extended Frege proofs and quasi-poly Frege proofs. And then there are other results which apply known techniques in kernelization, such as crown decomposition and sunflower lemma. And again, here we have to improve the kernelizations to make the length of the reduction chain logarithmic, because in kernelization that wasn't an issue. For us it is, and we're able to get polynomial size Frege proofs for dual coloring and extended Frege proofs of polynomial size for hitting set. But one of the more interesting applications of our result is to the area of computational social choice, specifically to the theorems of Arrow and Gabriel-Satterthwaite. And I'm not going to mention to explain these results more than to say that they're fundamental impossibility results on ranking a number of objects M by n agents, satisfying a number of axioms. And both theorems show that those axioms are incompatible. And the starting point of our work was some research in the artificial intelligence literature, specifically Tang and Lin, show that Arrow's theorem has computer-assisted propositional proofs, which basically reduce the general case N and M to one case of Arrow's theorem with N is 2 and M is 3. And so something similar happens for the Gibber-Satterwhite theorem. Okay, so this is quite similar to what has happened in our case with the Kneser-Lovász theorem. So it motivated us to take a look at the proof complexity of proving the unsatisfiability of such formulas. Now, I have to say that for these results, the results aren't quite as satisfactory, because the formulas that the propositional formulas that encode Arrow's theorem and Gibber-Satterwhite are quite large in N and M. They grow pretty big. So the point is that Tang and Lin gave data reductions of length theta of N plus M, and we managed to eliminate one of these parameters. We managed to make the reduction of length depending on the number of agents only, so to eliminate the dependence on the number of objects. And these data reductions that we gave have soundness that can be witnessed efficiently by efficient Frege proofs. So to conclude, our framework shows that such formulas have quasi-polynomial-sized Frege proofs, and polynomial-sized Frege proofs whenever the number of agents is fixed. We don't know at this point how to remove this dependency on the number of agents, and it's an interesting open problem. So to conclude, I hope that I've shown you that there are theoretical interesting connections between all these different areas, and that one can apply techniques from proof complexity, from kernelization to problems in proof complexity. There are other directions that are extremely interesting, and we're interested in exploring them. For instance, we've connected parameterized complexity to and proof complexity to kernelization. But there are other techniques in this area, such as iterative compression or color coding, that may be useful for obtaining efficient propositional proofs, and we'd like to do that. On the other hand, to some extent, our result, although stated for Frege proofs, could be easily applied to, it could be adapted to other proof systems. So in particular, we're especially interested in a system called SPR-. So this is a kind of a proof system that came from the SAT solving literature, and it's proof systems with no new variables, and it has its challenges because you're not allowed to do things that you're doing in extended Frege. So the relevant work here is by Hoyle and others, and also by Buss and Toppen in SAT 2019. Finally, a very interesting direction is sort of the converse one, and the question, an open question is, could we use lower bounds? Could we prove lower bounds on proof complexity for hard problems in parameterized complexity? So is it, in a way, can we connect hardness in a parameterized sense to hardness in the proof complexity case? So that's it. Thank you.